Okay, welcome back. This is the first in the series of videos on electronic structure. In class, we recently finished talking about the Bohr model, and just to sum up what we know about the electron at this point is that it has specific energies. So we know that for any element on the periodic table that the electrons have specific energies that they can exist in. They can't exist between energy levels, just in specific energy levels. In order to move an electron from a low energy level, like in this diagram from N1 into N2, we have to put in exactly the energy difference between those two orbitals. When the electron reaches an energy level which is higher energy, it's only there for a few moments before it'll return to its original lower energy orbital, and it releases light energy when it does that. Now, as far as the Bohr model is concerned, the main thing that we get from that is that electrons have specific energies. We still don't understand where the electrons are or what the actual electron structure of an atom looks like, and that's really the subject of today's video. So the question is, where are the electrons? And is there a way to visualize the electronic structure of an atom? All right. Here's a few facts we have to keep in mind because this question of electronic structure is actually a pretty hard one. So the first thing is that you have to remember that the electron is moving really fast, about 75% of the speed of light, and it's really, really small. So electrons act more like light waves than they do small particles like, say, a golf ball or a marble. And then one of the key things you need to remember is that the electron actually does not have a physical location where it lives. It doesn't have a house. It doesn't live in a jail cell. There is no physical location for the electron. So we have to figure out a way to sort of take something that's really abstract and think about it so that it makes sense. So here's what we're going to do. We're going to pretend that when your mom drops you off at school tomorrow, that we're going to take and attach a GPS locator to the back of her head. And for a month, what we're going to do is we're going to follow her everywhere she goes. And as she moves around, the information of her location is going to be sent to a satellite, and then that information is going to be transferred to a computer. And then what we're going to do is take all that information together and we're going to overlay it onto a map of the Phoenix area. So the month-long data might look like this. So she drops you off at school, and then she's going to be traveling around in this area because she's got to go to the store and who knows what, all of the different things she's going to be doing. Maybe she has to go to the bookstore. Maybe she's going to go to bath and bedroom or whatever the name of that store is and buy a new bed. She's probably going to spend most of her time, though, in a certain region of the Phoenix area. And when we're done with her traveling around at the end of the month, perhaps we have a tracing that looks like this. And what you can see is that it has a definite shape to it. She spends most of her time in this area because this is where she lives, and this is where you guys go to school. All right. Other parts of Phoenix she probably hasn't traveled into much because she has no reason to be there. Maybe they went to dinner one night. Maybe your parents went to dinner somewhere up in here one night or something like that. But the vast majority of her tracing is going to cover certain common regions within the Phoenix area. This essentially represents something that is not too far-fetched away from what an atomic orbital looks like. So we have basically a scan where the electron is spending most of its time, just like your mom spent most of her time in certain regions. If we want to know where to find her, then we know what we want to do is travel to some place on this map within this zone, and within this zone will be the highest probability of running into her. The reality is, if we actually went someplace in here, like let's say we stood on Chandler Boulevard and McQueen Avenue, the likelihood that we're going to actually see her drive by is pretty slim. But what this scan allows us to do is pretty much have an idea of where she spends most of her time. Now, if we assume that this is much like an atomic orbital, there are 4 characteristics that we can say about the condition of the electron in this orbital. The first is we can know the electron's energy. This is just like in the Bohr model. So in other words, the energy of the electron has to do with how far it is away from its proton or its protons. We can know the shape of the orbital, and in this case, when you look at the tracing, you can see that it represents something that is not too far away from this, and we call it a barbell. So we can know the shape of the tracing or the orbital where it exists. All right, we see that the tracing has an orientation. You can see how it extends on this XY plane. You can see how it extends in this direction. So this tracing that your mother created, or that the electron exists in, actually has a directionality to it. And I don't think it takes too much of a stretch to imagine this thing in a three-dimensional shape, in a three-dimensional shape, and it's facing a certain direction. So there's an orientation to it. And then finally, and this might be the thing that you've got to use this might be the thing that you actually have to use your imagination for. The electron spins like a top, and it has actually two options. It can either spin clockwise or it can spin counterclockwise. And what this does is that it actually converts the electron into a miniature magnet. Okay, now one last thing I want to say before I go, and then we'll enter into the next video in the series that actually deals with how we're going to apply this to the electronic structure of an atom. But coming back to the shape of the orbital, what you need to know about electrons is that we basically have two kinds of shapes in the world. The shape of the orbital can be spherical, and when it is, it's called an s orbital, or the orbital can be lobed, or it can be in the shape of a barbell, which I'm showing loosely here. Like, just think back to the last page that we were on. In the case of the lobes or the barbells, there's actually four different types. There's p orbitals, there's d orbitals, there's f orbitals, and there's g orbitals. Now, these orbitals hold a maximum of a certain number of electrons. In the case of the s orbitals, the spherical ones, and every single energy level will have one s orbital. The s orbitals hold a maximum of 2 electrons. In the case of the lobed orbitals, each type holds a different number. p orbitals hold 6, the d orbitals hold 10 electrons maximum, f orbitals hold 14, and g orbitals hold a total of 18 electrons.